today with strong acids and bases. When they dissociate, by definition, they dissociate completely. You like strong acids and bases. You like strong acids and bases because they're very easy to understand information about. Okay? AKA, if a strong acid completely dissociates, whatever concentration of your strong acid you start with will dictate how much of the proton is present, which means it also dictates the pH. So when a strong acid completely dissociates, it completely gives up all of its protons. All of what's present gives up all of the protons, which is why you can assume that the concentration that you start with of the acid is the concentration of that H plus ion, which is what you can use to get pH. You like strong acids and bases. There are 7 strong acids. You have seen them before. You were asked to try to memorize them then. Wouldn't be a bad idea to remind yourself that you're supposed to know what they are now. With the strong bases, instead of memorizing what they are, you're going to memorize the groups that really give us the strong bases in acid. Okay. Our strong bases do something similar. Now, instead of dissociating completely into a proton and something else, our strong bases typically have hydroxide groups, OH groups. They will also completely dissociate, meaning they will give off all of their OH. Now, once you have OH concentration, OH minus concentration, what can you do with it? You can get H from the KW equation. What else can you do? You could do POH, and then from POH you can get pH, right? Hopefully we've got that skill down. We're going to move into applying that information to equilibrium kinetics. So, from last chapter, you'll remember we used ice tables to indicate what was happening at the beginning and at the end of an equation's movement, right? We had that initial information, we had equilibrium information. pHs, POHs are all indications of equilibrium information. That's our major concept for the day. We're going to take that and we're just going to apply that to our Ks from our previous chapter. When we're dealing with weak acids and weak bases, we have to bring into account equilibrium kinetics. Reason being, they do not completely dissociate by definition. So you like strong acids and bases because you can assume that whatever the concentration is of the strong base is the exact same as the concentration of the OH minus ion that it's giving off. You don't have to do any equilibrium math to figure out POH or pH or any of that. You just have to plug in POH equals negative log of that OH concentration. With equilibrium kinetics, we're going to work with dissociation constants again. So Ks, when we write them for an acid, and this is a general equation, I want you to recognize some things about this general equation. First is when we are talking about the dissociation of an acid, we're adding it to water, okay? And liquid water is a pure substance that has no place in our equilibrium expression. So we ignore it. Second thing is, this guy over here is an acid. Why? You see the proton, right? By definition, it's going to give that proton up. That's from our Bronsted-Lowry stuff yesterday. Bronsted-Lowry stuff is going to go ahead and say, all right, here's my proton. You can have it, water. And creates the hydronium ion, which is an aqueous substance. Okay, remember that a lot of times we abbreviate this as H+. The other thing that's going to be left behind is that conjugate base of that original acid you started with. Okay? Now we take this particular dissociation equation for a general acid, and we're going to plug it into a K expression. Since we're doing this for an acid specifically, instead of writing Kc, what we're going to say is this is a Ka. So when we were doing problems in the past, in chapter 15, you saw a lot of KEQ, right? You saw a lot of KEQ. Well, we're going to kind of take things a little further, and we're going to talk about Ks related to acids. In this chapter, we're also going to talk about Ks related to bases. In a future chapter, we're going to talk about Ks related to things that are not very soluble, and we're going to say Ks related to solubility products. So things that don't dissolve very well get KSPs. And all of the principles are going to be the same. We're going to use ICE tables. We're going to make assumptions about what we're given. We're going to know that when we're given pHs or POHs, that we can use that information at equilibrium. Do you see where this comes from? Hopefully you remember equilibrium expressions always going to be products over reactants. And we never put that pure substance in there. That's why water's not there. All right. So this is our expression. Let's move on to what those K values mean. Before we do ICE tables, before we do the math with it, let's talk about what these things actually mean. Okay? Small values of Ka are going to be really, really big exponents, right? What they mean is that they are going to be weaker acids. So now instead of saying this is product favored or this is reactant favored, we're going to indicate the strength of an acid using a number. Using a number that does not require that we stick a pH probe into the solution. Okay? Kas are going to indicate from very, very big numbers, big being, remember, small exponents. 10 to the negative second is a big Ka. 10 to the negative 10th is a very small Ka. 10 to the negative second means stronger acid. 10 to the negative 10th means weaker acid. What our values mean? Okay. We're going to work with problems, and I'm going to introduce just kind of generally what they look like. We're going to do these together, okay? We're going to say that we want to calculate a K given some information. We're told the concentration of the acid, so that's going to be, of course, the thing that's on the bottom of our fraction. We're given the pH at a certain temperature is 2.38, okay? That's the information we are given, and we are asked to find Ka. So what's the first thing you should always do with our equilibrium expressions or our equilibrium reactions? Right, we want to get what we know written down. We want to make sure we start with an equilibrium expression. We were given that in this particular case. And I'm going to start doing the thing that I want you guys to be used to, which is switching out the hydronium ion with H+. Remember, they are interchangeable. And your book uses them interchangeably. We know pH, and we know the concentration of the acid is 0.10 molar. Could we write a balanced equation? Yeah. We know that this is going to be our reactant. We know our two products. In my particular case here, I could write this or that. Hydronium makes it easier to see where the proton goes. What am I missing on the left side? the thing that gets ignored. Everything is aqueous if it's in my expression. Okay. We're going to need equilibrium concentrations to get K values, right? When we talk about ice tables in the past, equilibrium concentrations are the things we plug in to our K expressions. At the moment, we can't make heads or tails of what we actually have. We know we were given information about an initial concentration, right? We were given this 0.1 molar for the acid. It's pretty much the only thing we know is a concentration that can fit somewhere in our ice table. Identifying where is half the battle, okay? In the particular case of the pH we're given, what can we do with pH? Get the concentration of H+, right? So let's do it. Up here, it looks like we've got 4.2 times 10 to the negative third. When a pH is measured, it's at equilibrium. So if you're given a pH, it's giving you information about equilibrium. Okay? In a problem like this, this gives you information about equilibrium. Always assume that. So that gives me H+ at equilibrium, doesn't it? That's this guy. Where does that 0.1 molar fit? Initial or equilibrium? What do you think? I would go with initial. It's the thing that's going to form the hydrogen ion that was then measured as a pH. So it's going to go here. Okay, now let's talk about the number sense. What would go here in our change, or what goes up here, I guess? Let's start here. Zeros across the board, right? Do we care about this at all in our equilibrium expression? We don't. It has nothing to do with equilibrium. It has nothing to do with our expression. Cross it off. It's there literally to help you see that the proton moves from the acid to the water to create the hydronium ion. All right, what goes in our change? On the left side? Minus X. What goes on the right side? On both, right? Okay, so what can you do next? We already know X, don't we? How convenient. If that's X, 4.2 times 10 to the negative third, this must also be this, right? Do you agree? Okay. What can we do over here? Subtract it. So what's 0.1 minus 4.2 times 10 to the negative third? Hey, look at that.
0.09.
Okay, we've got equilibrium numbers, right? No X's, nothing left over. What do you do next? Let's get Ka. Plug it into the Ka expression. Can you get that number?
Would we just square 4.2 times 10 to the negative third?
Yep.
Okay.
All right, so now we have an acid dissociation constant for the weak acid that we were starting with, right? So, comparatively, all right, remember that our strong acids completely dissociate every single time. This guy is weak, but it's not the weakest acid out there. Okay? We now have a measure for what's the difference between one weak acid and another weak acid. Okay? Another formula in this particular section talks about percent ionization. So if we wanted to figure out how much of the original acid actually dissociated, another measure of how weak is this acid, we take the concentration of the H plus at equilibrium, right? We got that from pH, and we divide by the original concentration, multiply by 100%. In this particular case, only 4.2% of the original acid that we started with actually dissociated. So when we say weak acids are a little more complicated, we mean it. This number for a strong acid or a strong base would always be 100%. Yes, ma'am.
How come it says HA instead of HC?
Oh, so this is the general form,
Okay.
and this is the one that we just did.
Okay.
Good question. HA is the default for any acid when they talk about it.
Okay.
That includes strong acids.
Okay.
So fair warning.
Okay.
A means acid, H is the proton.
Okay.
So percent ionization. Woo. If you can understand how Ka works, you're doing great. All right, another thing we can do with Kas, and we have practice problems that we will do together. These are just intro problems. We're asked the pH of a solution of acid given the Ka. So again, we're going to set up just like we've done with our equilibrium problems in the past. We're going to write out the reaction. What's the next thing we should do after we have a reaction? Let's start here. Let's write a K. Then let's make an ice table like we've done in the past, right? The whole shebang. It's a new problem. Remember, you ignore water in your equilibrium problems. Before we do anything, review from yesterday. Acid or base? Acid, which makes water the conjugate acid, conjugate base, conjugate acid, and then conjugate base. All right, well, I'm going to set up an ice table. I'm going to write a K expression. So what does my K expression look like? What goes on top? Thank you. Okay, we were also told that K has a value of 1.8 times 10 to the negative fifth. So if you had to compare the strength of this one to the one we just were working with, is this one stronger or weaker? Weaker, because the number gets bigger. All right. We're given initial information, right? Of one of these things. Now, what do we work with? Does this one matter? For the most part, when we deal with our acids, we're not going to have quadratics. So that's the gift in this chapter. Doesn't mean you won't have to do something solving with x's, but there aren't quadratic equations for the most part.
So how do you set up the
Products over reactants. You multiply your products on top, divide by your reactants, and remember we always ignore liquid water because it's pure.
okay, and then what's the
This one?
Just like there?
So this guy is H plus, is the same thing.
Oh.
Remember I said that I was gonna try to get you used to seeing H plus instead of H3O plus in the equations because they're interchangeable. Yes, sir.
So this is a weaker acid because it's only to the negative fifth?
Correct. This is weaker than the one we were just working with, is what we were saying. The one before had 1.8 times 10 to the negative fourth as the Ka, and this one is 1.8 times 10 to the negative fifth. That's all we were saying. Okay, what should we do next?
X's.
Oh, I might have lied about the quadratic. Just for this one. It'll be okay.
See, I feel like we're gonna say that.
I lied.
You said it, and I'm like, wait.
I was looking at it.
You're like, what?
Yeah.
I lied. I only solved one of them by myself yesterday that had a quadratic. The rest of them didn't. So it's 1 versus like 7. Yes, ma'am.
So for the first column, is it gonna always be like minus X?
Yes. Because remember, one of the things we talked about when we were doing equilibrium was reactants disappear, products have to appear. In this particular case, you know that it has to be that the reactant is disappearing because the other things are 0. You can't subtract from 0, right? Makes sense. Okay. All right, what do we do next?
Plug in what you know.
Plug it all into the K expression. Set it equal to 1.8 times 10 to the negative fifth, which is our Ka. Solve for x. Move that one over. And we will use my handy dandy quadratic equation solver. So you don't have to actually solve the quadratic. Thanks. I am that way. I'm so benevolent. Alright. But I need a quadratic to plug in. Anybody do the distribution and
X squared plus 1.8 times 10 to the negative x plus 5.4 times 10 to the negative 6.
minus? Do you mean minus?
Yeah.
What'd you say? 1 point.
Or the x squared plus 1.8 times 10 to the negative fifth x minus 5.4 times 10 to the negative 6.
Negative 6?
Yeah.
Fifth. I didn't hear your last word. Sorry. All right. So, 1. Then you said 5 point. All right, I got x equals 0.00231. I got positive and negative 0.0023 something. But the negative answer doesn't make sense, right? Okay, what do you do next?
Back to the ice table.
We just go back to the ice table, plug the numbers in. Was that the end of the problem?
No.
The goal is pH. So what are you going to do with that x value?
So, pH.
You're going to solve for the pH using that number.
Times it by negative log.
Negative log of 0.00231 is what?
2.6.
Is that what you got?
No.
That seems kind of low.
Don't you do 10?
No, we do negative log to get pH. We do 10 to get concentration.
2.636.
Okay. Okay. Using equilibrium. Okay, so let's see if we got it right.
Nothing.
Bum, 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 bum. They like to ignore their x's. You don't do that. 2.64. Nice job. They rounded. All right. From there, we have to talk about concept you read about, which is polyprotic acids. So when acids have more than one proton, okay? Generally, when acids have more than one proton, the first proton is the one that we care about. pH is generally only going to depend on that first proton leaving the acid. After that, it's not as likely to happen when it comes to our chemical equilibrium. Because in order for the second proton to pop off, the first proton has to leave and attach to something else, and then the second proton has to find a place to go. Not likely to happen when your reaction is happening, because at one point you're going to run out of a place to put your extra proton. Makes sense? Kind of like the flask gets crowded and no one else wants a proton, so that second proton has nowhere to go. So that's why we don't really use it to calculate pHs. It's also why you see this huge jump between the first Ka, meaning the first proton, that's what Ka1 means, and the second proton, Ka2. Okay? You're going to see a huge difference in their numbers. Much less likely to actually impact. And for things that have a third proton, don't even pretend you don't even see the third proton. Okay? So general assumption when we're dealing with polyprotic acids is the first proton is the one we care about to calculate pH. When it comes to bases, a lot of this equilibrium stuff is going to apply, but we're going to see that not all weak bases are created the same. Did you have a question, Joel? What?
Are we only going to be working on one base and one acid for this chapter?
For this particular chapter, we focus on one of the two things, and usually one of them is not water.
Okay.
Does that make sense? Good question. We will do acid-base chemistry towards the end, I believe, of this chapter, but we really dive into it next chapter. Okay? In a weak base, remember that a weak base, or any base, is defined as something that can accept a proton. We also like to define bases as chemical species that have an OH ion, right? That's not necessarily always true. In fact, a lot of weak bases do not always have that hydroxide ion. So instead, what we're going to be looking for is to produce the hydroxide ion by getting a proton to leave our water molecule and attach to our base. Okay? What we're going to see happening here is that our base might have protons, but those are not acidic protons. And if you draw the structure of NH3, you're going to see a lone pair on that center atom, that nitrogen. That lone pair is where that hydrogen can come in and attach. Now, NH3 is one of our very unique types of weak bases. Not all of them are going to have a structure that you have to recognize has lone pairs. Really, this is the one that we like to use to show you that this ammonia has that empty location for a proton to attach. Okay? This is unique. Again, in this particular case, water does act like the acid. NH3 is going to act like the base. We're going to see that that acid gives up its proton to the base and forms a conjugate acid with an extra proton, that acidic proton, and our conjugate base, which is our hydroxide ion. Now, when we measure pHs, POHs, we want concentration of either H or OH. This particular reaction does have OH in it, right? So we can use that same information we were talking about with acids on weak bases as well. We can do equilibrium kinetics on weak bases, is what we're saying. Okay? All right. An equilibrium expression for bases is going to look like this. Typically, bases are going to have a location for a proton to attach to. What's the thing that's not on the bottom because it doesn't go in the equilibrium expression? Water. Water is going to provide the proton that attaches to this base on the product side, and it's going to leave behind the OH ion. The K expression is now going to be Kb because we're dealing with a base. And a similar idea with Kas is going to apply to Kbs as far as what the numbers mean. The smaller the number, the weaker the base. Yes, ma'am?
Why would we not put water in the equation even if we use it?
So water is typically just because, well, for one thing, we don't measure concentration of water, right? We just assume it's a pure substance. So because it's a pure substance, it technically doesn't have an impact on the beginning of a reaction. Now it does get used and it does get broken apart, and that's kind of acid-base chemistry in a nutshell. But initially, it's just kind of there, right? Just like why we don't write in water when we talk about dissolving the salt. We just say aqueous. All right, so same thing with KBs. We can use KBs to find OH concentration instead of H concentration. We're going to use similar processes we did with our acids. Yes, Joel?
I feel like this is a silly question, but how do you determine which is Ka and which is Kb? I know B is base.
Right, so acid and base, right? It's not necessarily a silly question. The answer is you have to look at your reaction to determine if you're dealing with an acid or a base. A lot of times you're given Ka or Kb in some of these different problems. So you'll know, oh, this must be an acid reaction, or oh, this must be a base reaction. If you're not sure, make sure you're looking at the thing that's not water and applying our definitions. Is it a proton donor or is it a proton acceptor? Yes.
So, like, if we're looking to see if it's Kb or Ka, do we look at if it forms OH or H plus?
It's another good way to do it. With weak bases, yes, weak base will always form OH ion on the right side, whereas a weak acid will form the hydronium ion on the right side. It's a good question. One way to do it, but that's if you're given the equation. That's kind of, I mean, my answer is yes, but only in certain situations. Any other questions? All right. Because we can find OH concentration, you can see the path now, hopefully in your brain, to going from OH minus concentration to pH, right? You know you can use the pH plus POH equals 14. You know you can use KW. You know you can do a couple of different things to get there. Bottom line is if you're given an OH concentration, you can get, or if you get to OH concentration, you can get pH at some point. Okay, so here we are. We have a question. It says, what is the pH, pH, not POH, of a solution that is 0.15 molar in concentration of NH3? So we start with our balanced equation, right? We write our K expression, and we're given the K value for this particular reaction. What do we do next? There we are at equilibrium. When we do our math, they got x about 1.6 times 10 to the negative third. Hopefully you realize it's by plugging in, solving for x, etc., etc. that's my X value, which is my concentration of OH. What do I do next? Oops. Yeah, so two different ways we can do this. The way they did was they took the concentration of OH, calculated POH, subtracted it from 14 to get pH. You could do KW to get H plus concentration. Then you could just plug in H plus concentration into pH. Either way that you choose to solve, you should get the same or very close to pH. Now, does this pH tell us that this thing is basic? Yes. Does it tell us that it's a weaker base?
No.
Not really. This information is not usually very helpful. Interpreting pH is kind of a tough thing to do visually. Seeing a number doesn't really help you understand strength of acid base, okay? Because these values can be pretty high. You could have a weak base that has a pH of 12, 12.5, 13. Strong bases typically are very close to 14, right? 13.2, maybe 12.9. But kind of identifying where that weak base, strong base territory is using the pH scale is hard to do. And it has to do with the fact that the scale is a log base 10 scale, meaning a pH of 11 is 10 times stronger than a pH of 10. Right? So interpreting that number just visually is not something I would like you to do. I want you looking at values for Kb. I want you looking at percent ionization. Those are all indications that kind of give you a better idea of how weak is this thing anyway. Okay, with Ka and Kb, we can multiply them for a specific substance, right? So let's say we had the strong acid, nitric acid, HNO3, and its conjugate base, which is the NO3 minus ion after it's given up its proton. If we multiply those two Ks together, Ka times Kb, we should get Kw. That's just an aside. Kind of nice. Say again? A times B. All right. We're going to switch over to some practice. These are the problems that we're going to work on. The first 5 are the ones I'm going to do with you, and then you're going to do some on your own. Yes? Yes. Why don't you go ahead and take a 5-minute break? First hour's almost over. Doing great. This is the end of part 1. I will give you a part 2.